have quite the technology that I do downstairs when we have bigger classrooms, but I do try to record, so if these work, which they should, looks like it's working today, I'm going to be drawing, annotating on my iPad to go up here, so hopefully if everything goes well, you can go back and you can look at the lectures and you can watch them if you need to. So they will be under the Integrity Classes tab on Blackboard. Okay, a substance. We're going to talk about what a substance is. It's kind of the umbrella over two categories. Okay, a substance is a matter in which all the samples or all of the atoms have identical composition and properties. Okay, substances cannot be broken down or purified by physical means. Okay, so we'll look at more examples of what physical means actually means. Okay, but you can't physically separate anything in that substance. Okay, you can't physically pull apart the different atoms or the different things that make up the substance. Okay, one example of a substance. Okay, we have two examples. One is an element. Okay, and the other is a compound. So we already kind of touched on what elements are, right? Okay, so if you look over at the periodic table, okay, these are substances that cannot be decomposed into a simpler substance. Okay, why they're on the periodic table is because that is the simplest form of that atom or of that substance. Okay, so those are our periodic table of elements. Okay, and they cannot be decomposed by physical, so you may want to add that in there too, by physical means, because that's what a substance is, or by chemical means, by chemical reactions. So we can't physically take carbon and separate it into anything else. It's as simple as it can be. We also can't chemically change the carbon atom. Okay, so if we change it, then it's going to be a different element. So this is on the periodic table. So we've got one in here. You've got one in your book. If you don't learn anything through the semester, what I tell my students is if you learn a lot about the periodic table and the periodic trends and learn all the different things about the periodic table, then that's at least an accomplishment of some kind. So some students struggle with the math and the calculations. Okay, but being able to use a periodic table is very, very important. So it's really even your chemists at Harvard, they use a periodic table time in and time out. So it's very, very important. Okay, so the second type of substance is a compound. Okay, so we discussed, I think somebody said that, gave an example. We had two examples, I believe. A compound was H2O, so water. You guys gave that example. Somebody gave an example of salt, so NaCl. Okay, these are substances composed of two or more elements. Okay, so there's two or more of these combined together. Okay, through the semester we'll learn how they combine. Okay, in a definite ratio by mass. Okay, the only difference here with a compound, okay, it cannot be separated by physical means. I can't take water and physically pull the hydrogen off of the oxygen. Okay. But they can be decomposed or changed by a chemical change. Okay, so that's the difference in a compound and an element. An element cannot chemically be changed. It's the simplest form as it can be in. Okay, but a compound, you can actually break it down. So water, you can actually do what's called electrolysis, and you can separate the hydrogen and the oxygen, but it's an actual chemical reaction. Okay, a totally different category here is a mixture. Okay, these are two or more substances which have their own properties and composition. Okay, so these are not substances. Okay, and they can be separated by physical means. So I can physically separate the different components of a mixture. Okay, so these are just some obvious examples here. Okay, you have a homogeneous mixture. Okay, that means basically that it has no distinguishable parts, that you can see through it. Okay. Examples would be like salt water, air. Okay, we can't see the different components in the air, okay, but it is a mixture of different gases. Okay, heterogeneous mixtures, these are ones where you can see the distinguishable parts. Okay, so if you think about physically, if I wanted to, I could sit there and I could pull all the different parts out and I could physically separate everything in this bowl of soup. Okay. What about for orange juice? You think it's a homogeneous or heterogeneous mixture? That's kind of another one of my duet. Okay, exactly. It could be homogeneous. Okay, so if we think about, do you like to drink your orange juice with pulp or no pulp? No pulp, me too. So mine is homogeneous, okay? But if you're one that likes, if you had lots of pulp in there, then it would be more heterogeneous. So this one can actually be, this one looks pretty clear. I can't distinguish any parts in this picture here. So this would be a homogeneous mixture. Okay, so here's some examples. So we're going to label these as a mixture, substance, compound, and or an element. Okay, so we may label them as both. Remember, a substance includes an element and a compound. Okay, so if it's a compound or an element, it's also a substance. Okay, so I'll give you just a few minutes to look at this, then we'll go through them. Okay, so look up here. What you guys label the first one as? Okay, all right, it's copper, 29. Go over here, look on the periodic table, copper, 29. Okay, so it's an element. If it's an element, it's also what category does it fall under? A substance, exactly. Okay, so element and substance. Okay, what about this? This is a pretty easy one. Okay, mixture, obviously a heterogeneous mixture, right? Okay, what about this beautiful wave? Makes me want to go to the beach. Okay, he said mixture. Okay, so assuming that it's just the salt and water, it's very clean ocean water. Okay, it would be salt and water. Okay, so we have a mixture, and this would be a homogeneous mixture, right? Okay. Do what? Also have elements there. Okay. Okay. You have water, so you have a compound, and you have a salt. You have two compounds that are mixed together, though. Okay, so that makes it a mixture because there's two distinguishable parts. Okay, so let's think about this real quick. One of the main things about a mixture is the fact that we can physically separate it. Okay, has anybody ever physically separated salt and water? Okay, so how could we do that? So what could we do in a lab or really anywhere on your stovetop? Yeah, you evaporate the water and leave behind the salt. Okay, that's what makes this a mixture, not a substance, because we can physically separate the two. Okay, one other way that you can physically separate things is by filtering. Okay, so that's another, you wouldn't have to necessarily do that here, okay, but that's another physical way that we can separate the two. Okay, so this would be a mixture, not a substance. Okay, what about here? All these molecules here. What are those? We've got H2, O2, H2O. They're compounds, exactly. So they're two or more of, well, some of these are just one, but they're two of the same, so these are more obvious, but they're compounds. So we have two or more elements from the periodic table chemically combined. And we're going to look at how they chemically combine through chemical bonds actually in this unit as well. Okay, but compounds also fall under what category? Substance or mixture? Substance, exactly. And what about here? What does this look like? Okay. What do you think this is a picture of? Oil and water, exactly, which we all know separates, right? Okay, so we have a mixture of oil and water, okay, and that would mean that this would be a heterogeneous mixture, right? Because we have two distinguishable parts that we could separate. Okay. All right, any questions on that? That kind of ends kind of the terminology for Chapter 1. Any questions? Okay. Okay. Now we're going to kind of switch gears and we're going to start talking about numbers. Okay, this is super important for chemists, okay, or for scientists in general, because we're constantly observing, we're measuring, getting our experimental data, and we have to record it. Okay, and so we need to be able to record our data, and if I'm collaborating with a scientist in China, that he understands exactly what I've recorded, my units, and he understands to what precision that I was able to measure, whatever the chemical or whatever the reaction or whatever I'm doing in the lab, okay, that we are on the same page. Okay, so this is extremely important. This is an international way of recording your numbers. Okay, so wherever you go in the world, they will be teaching the same thing. Okay, exact numbers. So we got to go through once again some terminology of numbers. Okay, these are things like 1 dozen. That always means 12 things. Okay, so it means that we have an infinite number of what we call significant figures. Okay, we're going to talk about in detail what a significant figure is here in a few minutes. Okay, so it's like we have 12.0000, could keep going on, things. Okay. Has anybody gotten as far to print off this from Blackboard, the conversion factors sheet? Anybody? Okay, well, I'll send these around and save you having to print off. I think I have enough. But these, before I pass them around, are also exact numbers. Okay? So it says 1 pound is equal to 454 grams. Okay, this is an exact number. Okay, these have been recorded for you in tables, in your books. And these are also examples of exact numbers. Pass them around. Okay. All right, 2 more points here. So accuracy versus precision. Okay, you may already know the difference between these two. We're going to go over it anyways because we want to think of this with respect to our experimental data in the lab. Okay, accuracy is how closely your measured value agrees with the true, correct value. Okay, that's how accurate you are. Okay, precision is how closely your individual measurements agree with each other. Okay, more times than not in a chemistry laboratory, granted we don't have time with you all to repeat experiments over and over, but for instance, when I was in a research laboratory, when I do one reaction, it was automatic that I had to do it at least 2 or 3 more times to see if I got the exact same data from that reaction. Okay, so one time really isn't enough. So you do it over and over. So you do more trials than just one. Okay, so if we're in the lab, let's say you got 5.60 grams of whatever substance you were taking the mass of. Okay, and then you did the same thing again. You got 5.60 grams. Okay. Did it a third time. This time you got 5.59 grams. Okay. Would you consider that your 3 trials are fairly precise? Think so? Pretty close? Okay. Okay, so we would have good precision here. Okay, but then you come to me and you say, okay, this is the mass that I got. What is the true mass or value for the experiment that you're doing? And I was to tell you that it was 7.00 grams. Okay? You were precise, but were you accurate? No, exactly. So that is the difference. So you had, if this value would have been 5.60 or 5.61, then you would have been precise and accurate. Okay? So that is the difference between the two. Okay, just until they come around. It probably just wasn't stapled, so we're not even going to be really using them much today. Just be sure you have them on Tuesday. Let me check. I was talking. Okay. Somebody else probably got the top part, so she probably got the top, and that goes together. Yeah. Okay, so going back to what I was saying about how if I measure something in the lab or get my final result and I need to collaborate with whether it's your lab partner, okay, or whether it's your boss, whether it's somebody, way, way far away, okay, we have to be on the same page, okay? So we have to record what we call significant figures, okay? Significant digits mean that these are the measured numbers, okay, because that's a big part of chemistry. We have to measure things. Okay, so these are measured numbers that you obtain when you measure a quantity, such as height, weight, temperature, can be all kinds of things. And these are the digits that you believe to be correct, okay, by the person that's making the measurement. Okay. So significant digits, we have some kind of rules that go along with these. You have to be able to recognize what's a significant digit and what is not a significant digit. Okay? So if we look here, the first rule is that all non-zero digits are significant. Okay, so if we have the number here, we have 1, 2, 3, 4, 5, 6, 7. We have 7 significant digits. Okay? All right, the big thing, the discrepancy becomes when we have zeros. Okay, so this is where we have to have more rules. Okay, so leading zeros are never significant. I'm not real sure forget what your book calls them. This is what I call them because to me it makes sense. Okay, these leading zeros that are out in front of a non-zero digit, okay, these are not significant. Okay, so if we look at this number here, how many significant digits do we have? We have 3, exactly, because none of these zeros leading are significant. Okay? Trailing zeros may or may not be significant. So this is the one that most students take a little bit longer to get. Okay? If you have a decimal place, okay, so your trailing zeros are going to be ones that follow the non-zero digit. If you have a decimal place, then all of the zeros or whatever's after that are significant. Okay? You think about it as that decimal place is saying, you put that decimal place there saying that I didn't just measure 3, I measured to the 10th, 100th, 1000th place. Okay, so it's kind of holding the place for the rest of these zeros. Okay, so we have 4 significant digits. Okay, if there is no decimal place there, all of these trailing zeros are not significant. Okay, so we only have 1 significant digit here. Okay. I call these sandwich zeros because they're in between 2 non-zero digits. They're always significant. Okay, so both of these zeros right here are significant. So we have 1, 2, 3, 4, 5 significant figures. Okay, this is underlined. You want to be sure you remember this. I'll remind you on Tuesday. Okay, so when you are measuring in the lab, that's all you're going to be doing on Tuesday, you always want to measure to 1 estimated digit. Okay, we're going to do an exercise here in a second for you to actually see what this means. Okay, but that is one of the most forgotten, and then usually students might do it on the first lab and they forget to do it later in the semester. Okay? All right, if you have to you need to remove any doubt of how many significant digits you have, you can always put your answer, especially large or small numbers, in scientific notation. Okay, so that's what's been done here. Okay, the numbers that are out front before this exponential here, that's how many there are. So 2.40, there's 3 significant digits in this scientific notation form. Okay, so how many significant figures are represented in this number here? Okay, let's classify the zeros real quick. Okay, so our first one, reading left to right. Okay, is it a leading, trailing, or sandwich zero? Leading. Okay, so what was our first rule about leading zeros? Significant or not? Not, exactly. Okay. All right. What about these 2 zeros? What we classify them as? Exactly. So they are going to be significant. Okay, and then what about these zeros here? Okay, they're trailing. They're at the end. Okay, so what do we have to go look for to see if we have a decimal point present or not? Okay, if we do, then these zeros are significant. Okay, so if we add these up, 1, 2, 3, 4, 5, 6. We have 6 significant figures. Okay, I'll give you a minute here to identify the significant and non-significant zeros, or if you want, you can just tell me, go through and think about how many significant digits there are in each of the following. These leftovers. Here you go. One of y'all can keep that one. I don't think I have a stapler. Here's your paper clip. You want me to keep it together? Okay. See if you got this. So this goes through the explanation. Okay, so for the first ones, the zeros preceding or in front of the 2 are not significant. Everything after is, because we have a decimal point. So did everybody get 4 significant digits? Okay, for this one, all of the zeros, or we only have 1, but all the numbers here are significant. Okay, because this one is in between 2 non-zero digits. Okay, so we should get 5. Everybody get 5? Okay, what about for the last one? What did you guys get? Anybody? Remember what it was? Or did you do it in your head? Okay. Yep. Very good. Okay, so for this one, we only have 1 0 that's significant because it is in between the 2 non-zero digits. Okay, and then our zeros that are trailing are not significant. Okay, so why is that? Why are the trailing zeros not significant? Right, there's no decimal point. Okay, so we end up with 4. Okay. Hopefully everyone has had scientific notation. You should have learned how to put your answers in scientific notation in the algebra and the classes that you've had prior to here, but just in case, and this is basically just for you to kind of go back to if you need it. But for really small numbers, so this is just a really small number. This is the diameter of the chickenpox virus. Okay, it's a really small number. So for convenience, okay, also for organization, when you have a really small number or a really large number, it looks, in presentation even, it looks a lot better and is easier to look at when you put it into scientific notation. Okay, so really small numbers, you're going to move the decimal place over. okay, until you move it past the first non-zero digit. Okay? And then for real small numbers, you're going to have to the -7. So when you move here, you move to the right, okay, and have a negative there. Okay, I still see some mistakes, even with later in the semester, we'll actually put a positive there. Okay, so positive would mean you'd have a really large number. Okay, so these are just some kind of random facts, I guess, that I've looked at in scientific notation. The first one, definitely, so that's the volume of gasoline used in the United States each year, okay, in liters. That's definitely a large number, so it looks a lot nicer if we put it into scientific notation. Okay, so you can go back, like I said, for practice. If you want to put all these in scientific notation, would be good practice for you. Okay, the diameter of the Earth, that's another one, large number there. As for 500 seconds or 68 kilograms, honestly, I don't usually put those in scientific notation. You can, usually to the third power or -3rd, I will, but those, to me, not really any more convenient. Honestly, the 6.8 times 10 to the first looks really more work than it needed to be. Okay. For, let's see, we got the mass of a hummingbird, so that's usually about when I will start to the -3 here, start putting in scientific notation. Okay, and there's the chicken pox, and then one more, so that's a really small number there, so obviously looks a lot better in scientific notation. A lot of your calculators will, especially for numbers like this, I don't think we'll ever use a number that small, but we'll usually put it in scientific notation for you anyways. Okay, so we talked about the rules of significant figures. So is there any questions over those before we start to actually use them? Okay, so the reason you have to learn the rules first is because now we have to know how to use them. So we have to measure and we have to record the correct number of significant figures. Okay, so here is a little exercise we're going to do. So we have a piece of black paper and we've got rulers on each side. Okay, what's different about these two rulers? Anybody see anything different? Okay, now this ruler up here on the top is calibrated more precisely. Okay, this is going to be a situation you run into all the time in the lab. You're going to may use one instrument that is more precise than another. Okay, for this ruler, we really have no calibration here, right? So we really kind of have to estimate what's between here and here. Okay. Okay, so the first thing I want you to do, okay, this is just kind of blown up on, this is a piece of paper, just kind of blown it up so you can look at it closer. Okay, I want you to think about how long the paper is. So I want you to measure how long the paper is to the best of your ability, okay, and always measure to one estimated digit. Okay, so what that means, estimated means that this ruler is calibrated to right here, right? Okay, but from this point to this point, I have to estimate, right? So that is my estimated digit. Okay, so you measure to here, and then there's a point where you have two calibration points, and you've got to measure or estimate what's in between there. Okay, so that's your estimated digit. Okay, so I want you to write this number down because you're going to need it as we keep going. What are some of the numbers you guys are getting for this? What did you record? Hopefully everybody recorded 13 points something, right? Okay. So what did you get, Leanne? So you rounded to 13.4. Okay. Anybody else? Okay. Okay, so good examples. Okay, so you said 13.35. That's what I wrote down. You said 13.4. Okay. The only thing, Leanne, that's wrong with your number is that you didn't use your estimated digit. Okay. So when you measure, you want to measure to the calibration point of the instrument and as accurate as possible that instrument will allow. Okay, on the next time on the ruler, you're going to have to go just to the 10th place. Okay, but here we were able to measure to 13.3 and then estimate. Now, it's not wrong if you estimated a 4 there, or if you estimated a 3, or that is your estimated digit. Okay, so personally, I picked 13.35. That was just how I saw it looked, halfway between the two. But you want to use all of the numbers that the instrument will allow you to use. Okay, so you can be as precise as possible. So you want to go out, so you want to have 4 significant digits there. Okay, now we're going to look at the width. So this time our ruler is not calibrated. Okay, so it's going to change things a little bit. So as far as we can see, it's calibrated as just the 8, right? So we have to estimate this whole distance here, okay? So I estimated 8.2. Okay, that's my one estimated digit, was that 2, okay? Somebody may have estimated 0.3 or 0.1. Okay, you cannot say 0.15 because you don't have the calibration there to insinuate that you have a 1 here. We don't know where that tick mark is because it's not present there. Okay, so I want you to take both of your numbers and I want you to find the area. So you take the length times the width that you just wrote down, your 2 numbers. Okay, and then the person next to you or whoever, I want you to compare your answer. So the area that you get, taking the length times the width, compare your answer to the person next to you. It looks like, from what I'm seeing, that 109.47. Okay. Remember, we have units. We'll talk about units later, but okay, did anybody get 109.47 is your final answer? Okay, what are some other numbers you guys got? Whoops. Okay, 108.54. Okay, hers is quite a bit different because she didn't estimate as far as you should have for the first one. Okay. All right. What did you get there? Okay. Okay, so you probably use a little bit different number on that second measurement. Maybe. What were your two values? Okay. For that first one, you want to estimate that one digit. So you'd want to have 13.35 for whatever you estimate there. Okay, so you want 4 significant digits there. Okay, anybody round differently? What'd you get? Okay, we got a 110 over here. Okay. All right, so if I'm trying to collaborate, this is just one class of 30, I guess. Okay, we got some pretty different numbers, didn't we? Okay, so in the scientific world, this can be a big difference. For this experiment, obviously measuring the length of a piece of paper is not that big of a deal. Okay, but in reality, it can be. Okay, so we have the rules. We know what significant digits are. Okay, now we have to know how do we record them when we're doing a mathematical calculation. Okay, so we have to have rules for multiplication and division. Okay, and we're also going to have rules for addition and subtraction. Okay, so here we multiplied. Okay. This is actually the easier of the two rules. Okay, when you multiply and divide two measured numbers, or just two numbers in general in chemistry, most all of them are measured in some way. Okay. The product, so your final answer, is going to be rounded, okay, to the number of significant digits that is the smallest number of significant digits in your multipliers. Okay, so if we look here, we have 4 significant digits, and here we have 3. Okay, so our answer has to have only 3. Okay, so the smallest number of significant digits in your multipliers, that's how many significant digits you have in your answer. Okay, so if we look at this one, these are just random numbers. We're going to go back and look at your measured numbers here in a second. Okay, for here, we have 5 in one of our measurements, but we only have 2. Okay, so we have to round to 2 significant digits. Okay, so if we go back, I'm just going to use, and yours still may vary a little bit, but if I go back, so I chose 13.35 centimeters times 8.2 centimeters. Okay, I got 109.47. Oh, it shouldn't be centimeters. What am I talking about? Inches, sorry. Inches squared. Okay. So what are we going to have to round to? How many significant digits? We've got 4 and we've got 2. Okay, so our answer has to have how many? 2. Okay. All right, so what do you think we're going to end up with here? Exactly. Okay, so you go to that second posable or probable significant digit, okay, and then we go over here and we have a 9. Okay, so that means we're going to have to round up. Okay, so that gives us 110. Okay, what if I did this? How many significant digits do I have now? 3. Okay, so you have to leave it without the decimal place. And now we have 2 significant digits. We have 2 ones, and then this 0 is insignificant because we have no decimal place there. Okay, so correct would be okay. Any questions on that? Okay, we have a rule for multiplication and division. We also have a rule for addition and subtraction. So now we're going to take your measurements that you already used, and you're going to find the perimeter of the paper. So hopefully you guys all know how to do that, but if you don't, you take each side, you add the 2 lengths and the 2 widths. So you take your 13.35 plus 13.35 plus 8.2 plus 8.2. Okay, so what were some of the numbers? Don't pay attention to this here. Okay, what are some of the numbers you guys were getting for the perimeter? Okay, 43.1. Okay. Anybody else? Why did you choose to have 3 significant digits? Just because? Okay. Okay, anybody else get 43 point anything different? Okay, you got 43.3. Okay, did anybody just get 43? Okay, basing their answer off the fact that you just had 2 significant digits, right? So you might have to have 2. Okay, that would be a good guess. Anybody else have one they want to? Okay. For addition and subtraction, okay, this is a more subtle rule. So this is one that all the time students will come up to the lab and they'll say, well, I'm supposed to have this many significant digits, and then I remind them of the addition-subtraction rule. Okay. You're actually not going to be looking at the significant digits, okay, for addition and subtraction. You're looking at the decimal place. Okay, so you look at all your add-ins here, and you see that for this example, that we only go to the 100th place here. Okay, these other ones are more precise. We go out further. Okay, so our answer goes out to the 100th place. Okay, so we're not classifying these per se as significant digits. Okay, we can say yes, we have 3 significant digits in our answer. But how we arrived at that was looking at the decimal place. Okay, so we're looking at how far we go out on the smallest number, basically, okay, or that's measured the least precisely, okay, and that's the answer. Okay, so if we look here, we go out to the 10th, 100th, 1000th place. Okay, so our answer, we go out to the 1000th place. Okay, so if we were to correctly come up with the perimeter, so if we take, I'm just going to use my numbers again. Okay. So I know I get 43. Okay. I'm going to record it as 43.1. Okay, the reason I do this is because we go to the 10th place. Okay, that's our smallest number here. And so the answer goes out to the 10th place. Okay, so you can't look at this as significant digits, because if we did that, then we'd only be able to have 2 here. Okay, but we have 3, so we look at this number there. Okay, any questions on that? I'm recording numbers. There's a homework I'm going to show at the end of class. We may have a few minutes to work on it, but you should be able to start working on that worksheet. So it's got scientific notation, it's got significant digits, addition, subtraction, so you should be able to go ahead and start on that, so to get some practice before next Tuesday. Okay. On Tuesday, we're actually going to look at converting from one unit to another, but the first thing we've got to talk about are units. So what are units and why do we use them? Okay, most all of your chemistry measurements are not just going to be a number. You're not just going to say 111 or 104. You're going to follow that with a unit telling yourself and your lab partner or whoever else, or me, okay, what you are measuring. So were you measuring the mass of something? Were you measuring the length of something? Okay, so you have to report a unit. Okay, so I do count off if at the end you might have done the calculation. I don't count off much, but it is important, especially here in the beginning, that you record to me what you found. So if you just put 104, I don't know what you were doing. I probably do, but I'm assuming because I know what you were supposed to do. Okay, but if you have, so length, this is the international system, length, mass, time, volume, temperature, amount of a substance. So these are the different quantities that we measure in chemistry. Okay, and these are called the International System of Units, okay, also known as the SI units. You'll see that in your book. Okay, and these are kind of the standards. And this is what this committee got together, and they said, okay, when we collaborate with each other, we're talking about length. It's going to be in the unit of meters. Okay, we talk about mass in kilograms, time in seconds, okay, volume in the cubic meter, and so forth. Okay, the only country in the world that doesn't use this is the United States. Okay, so I guess that we like to be different as far as what we use on day to day, even using Fahrenheit and versus Celsius, we differ in that as well. Okay, but for chemistry, we do use the International System of Units. Okay, so we use Kelvin, so this is even around the world, use Kelvin. So we do use the International System of Units. Okay. A lot of your units may have, or your measurements may have a prefix that comes before. So if you think about a kilometer, or if you think about a centimeter, okay, so we're talking about the prefix before the units that we just looked at on the previous slide. Okay, so you don't have to really memorize these. You'll start to get familiar with these as you move on through the course. Mega, that basically just means that's going to be a capital M. That just means if you had a mega meter, okay, that means that you have times a million of a meter. Okay. If you have a kilometer or kilometers, what I say, either way works. Okay, 10 to the third, that means you have 1,000 times a meter. So that's one that you'll use over and over. So you always want to think about 1,000 when you hear the prefix of a kilo. Okay, deca, not used as often. Okay, but it's times 10. So if we're talking about a meter, it'd be like times 10 meters. Okay, and then a decimeter, this is basically 1/10 of a meter. Okay, so now we had really large numbers, now we're going to smaller numbers. Okay, everybody's heard of a centimeter, I hope. Okay, so this is 1/100th of a meter. Okay, so we can replace this not just with meters, you can have centigrams, or you can have all different sorts of endings there. Okay, so a millimeter, okay, or a milliliter, we'll use that a lot. Okay, this means 1,000th. Okay, so that's one you probably do want to get in your memory bank if you didn't already know that one. So we usually use it actually as a milliliter, so we talk about milliliters a lot. Okay, and then we just get smaller and smaller, so we don't use these as much. These are really small numbers, so like a micro, that would be the symbol for it. So a micrometer would be 1/1,000,000th of a meter. Okay, so it'd be really small numbers as we keep going down here. Okay, the last kind of terminology for measurements that we're going to talk about today is the difference between mass and weight, these two terms. Okay, they are used interchangeably. I use them interchangeably. A lab assistant, we try to be, but it just happens. But there is a difference between the two. Okay, mass is the measure of the quantity of matter in a body. Okay, so if I take my body and I put it on Earth, I'm going to have the same composition and mass that I do on the moon or on Mars or wherever. Okay, gravity does not play a part. Okay, so when you measure the mass of something, you have to do this on a balance we have those we call them balances in the chemistry lab. Okay, they're a lot more expensive than your typical scale. Okay, they have a counterpart to them that kind of subtracts out that gravitational force. Okay, and so when you put something on, and I will accidentally say weigh, but I should say that you need to determine the mass of your sample on the balance, not weigh your sample. Okay, it should be determine the mass of it. Okay. Weight, on the other hand, is the measure of the gravitational attraction for a body, and this varies with the distance from the center of the Earth. Okay, so this is different. My weight's going to be different here than it is on Mars or on the moon. Okay, and so this is measured by a scale. So when you get up in the morning, you step on the scale, and that is your weight. That is not your mass. That is what you weigh based on the gravitational force and attraction on your body. Okay, any questions on those two? Okay, if you've got, hopefully you got everybody get a conversion factor sheet printed. Okay, that is also on Blackboard. It's under the unit as well as under the handouts, I believe. You will be given this also with your exam. Okay, so I don't require you to memorize all this. These are common. You can find them anywhere if you ever, need them. So you don't have to memorize them, but we do have to know how to use them. Okay, so all of Tuesday we'll be looking at how we can convert. Okay, a lot of you already do that anyways. If you have to convert, many times I've been given a measurement in inches and I have to convert to feet. I mean, you do that in your, everyday life. Okay, so we're going to be doing that on Tuesday, looking at, of course, more complicated situations as well. Okay, if you'll give me a second, I'm going to pull up. I don't have the browser on this computer. It's crazy. Okay, while I'm pulling this up, is there any questions over today? Anybody? So everybody's going to get all their measurements right on Tuesday. Hope. Okay, you may have already seen this, may already have it printed out, but I'm just going to show you, just be sure you know what your first homework is. There's homework number 1. If you haven't seen this, like I said, my end looks a little different than yours. Okay, but this is Unit 1, tells you when it's due, February 11th at 9:30. So everything in here is due if it's labeled with the homework number. Okay, so you have homework number 1. That's what I'm about to show you. There's that conversion factor sheet that I already printed for you. Okay, there's our next chapter. We're actually going to move from chapter 1 to 4. I just like that sequence better. And there will be homework 2. You can actually, a couple problems here. This is kind of a quiz, but that doesn't mean, I call it a quiz, it's in a quiz format. That doesn't mean that it's going to be turned in the same way. You're going to turn it in the same day. It's not really different than just homework. Okay, but on this quiz, you have some chapter 1 problems. So you can also start doing a couple problems from the quiz after today. So we're going to pull this up. Okay, so this first part is converting, so you won't be able to do that yet. You can go ahead and try. Some of you may have done that a lot previously. Okay, so that's all converting. Okay, so here's something that we can start working on. Okay, so just for the remainder of the class, if you don't already have this printed out, you can start working on these. This is scientific notation. I can scroll it down. This one here is just telling me how many significant digits there are. Okay, so this is a great time to ask questions if you have any. Okay, and we'll just do this for a few minutes before class is over. No, you just bring it to class. Yeah, on that 11th, you'll just bring it to class at 9:30, and that's when I'll check it. Colton here. Alexander, Daniel Mason, Brenna, Casey Scott, Fionn, Reed, Terry, and if you weren't here on Tuesday, I have a syllabus if you need it. Be sure on this part, for working ahead though, that you show me all of your, so like on Tuesday I'm going to show how I want it formatted, like, step by step kind of. So if you do that on the exam and you miss it, then you don't get any partial credit. So, but yeah, but you can keep it till the 11th. these when you're expressing in scientific notation. So if you start, if the number you're given has 3 significant digits, then your answer needs to have 3 significant digits. If it has 2, it needs to have 2, 4, so whatever you start with. So here you'd have 8.62 times 10 to the 1, 2, 3, 4, 5, I think that's 6, times 10 to the negative 6. Or that's 5. That's 5, actually. Sorry, I'm kind of wrong. 8.62 times 10 to the negative 5. Do I? Yeah, I can't have to have it on paper to. Sorry. Okay, and when you're rounding up here in 14, so if it says to 3 significant digits, then go to that third number and then round down or up from that number. So everybody got 14 now? These ones are probably the hardest ones here. That's what I would do, yeah. It doesn't, you can, I would multiply first, and then if you have, say you have 2, so you have to have 2 here, then go ahead and multiply this out, get your number, and then divide. Yeah. Yeah, and you have, yeah, because you're going to end up having, you can only have 2 significant, that's right. Probably want to go ahead and have your calculators for class, every class. I'm not saying we'll use them every time, but go ahead and bring them because you will not be able to use your phones on exams either. So you need to be able to get familiar with your calculators. All right, you guys can keep working, or if you're done or whatever you're free to go. You guys have a good weekend. If you have any questions, I can come around to. Okay. I did get you on roll today.
Ma'am,
What's your name?
Mauricio Garcia. It was kind of a last minute thing when I enrolled.
Okay. I just want to be sure I've got you on.
Yes, ma'am. I'm probably, this first month of class, I'm gonna be here Tuesday, but I gotta do some swapping around as far as scheduling at work or whatnot. But I'm gonna try to be here every day. But there may be another day or two that I miss just due because it was last minute. I didn't think I was gonna have enough money to come to school.
Okay.
But
Okay, just be sure you read through this. The biggest things are, here's your exam tentative schedule. Here's your tentative lab schedule.
Yes,
So
ma'am.
1 to 3. So these are, all mandatory.
yes, ma'am.
This is the makeup policy. So basically you have to have documentation for any missed exam
Yes, ma'am.
or, and then homework, you get half credit no matter what if it's late.
Yes, ma'am.
And I won't take it after May, so that's a long time from now. But if you do miss lab and you have documentation, this is who to contact for that. So that's kind of the main things. But yep, and we're just doing chapter 1. So, and we'll have lab on Tuesday. Hey, yes. Okay, and yours is the same. Here's your tentative exam schedule, and here's your lab schedule. So these are all mandatory. I don't know if you heard me talking to him, but be sure you read through that as well. So you're welcome. Yes, ma'am.
You would be able to check out homework to see if it's right before or after it's due.
Okay. You can bring it to me before, but what I do is I'll check it that class before the exam, and then I'll post answer keys and have everything written out so you can check your answers before the exam. But if you need me to look at it even before that, just let me know. Mm-hmm. Hi.
I emailed you about my son today.
Okay. Yes.
I have pretty much over it.
Okay. You have one.
Yeah.
Okay.
All I need to do is watch the lab videos.
Yes, those you have to do the safety and the measurements one on Tuesday, or before lab, and then just be sure you read all about the makeup policy and all that in the syllabus. Okay, so that's kind of the main point, and your tentative exam schedule and everything's in there too. So, okay, thanks.
I have a question about number 14. Is it E? Yeah. The first zero before the decimal point's insignificant, so you just count 3 significant numbers, so the answer would be 0.027. So there are 3 significant numbers after the decimal point.
Okay.
I would think
Yeah.
like the first zero is insignificant, but then like the second zero, you can only round to 3. Right?
Yeah. So you're round to 3. So if you have 0.0270036, okay, so it's telling you to round to 3. So there's your third one, and then it's not going to round up, so you just get 0.0 is not significant. Yes.
But I didn't know if I had to roll the scale down because it doesn't have anything after.
But it's following a decimal, remember? If it follows a decimal, then it is. Yep, that's one of the most missed or forgotten ones, is because if there was no decimal, then that would be true, that it wouldn't be. But since there is, it is. All right, now I've got to switch gears to organic.